So this screencast is talking you through angular kinematics, which is progressing from the linear kinematics that we discussed in your first lesson. So last week you all went over muscle pairings and also reciprocal inhibition and anatomical movement. So I will screencast a PowerPoint for that as well. But you did cover that in anatomy, so that was just more of a recap of your knowledge, whereas this is development of what we learned in week 1, so hence why you're covering it this week. So there's some key terminology you need to know for angular kinematics. So first of all, just a quick recap. So linear kinematics was to do with linear movement, so that was where the body stays upright. With angular kinematics, it's when you rotate over an axis. So for example, completing a forward roll or a somersault, because the body is rotating through an axis. So the 5 key terminology for angular kinematics are angular distance, angular displacement, angular speed, angular velocity, and angular acceleration. So what I'd like to do at this point is pause this video and split into groups of 5, and each group is responsible for finding a definition of each term. Okay, so my definition for each term is angular distance is the sum of all of the angular distance travelled. Angular displacement is the difference between the starting and finishing angle in a given direction. Angular speed is the rate at which a body moves from one angle to another. Angular velocity is the rate at which a body moves from one angle to another, taking direction into account. And angular acceleration is the rate at which angular velocity changes with respect to time. So what you should first notice about these definitions is that they are very similar to their linear counterparts. It's just for taking angles into account this time. What would be good for you and to develop your scholarly activity is to find a really good biomechanical textbook. So maybe Bartlett's book from 2007, or more preferably Hayes' book from 1993, and finding out the definitions that they have given to these terms. Just a quick task. So angular distance and displacement. So what I want you to imagine now is I've taken my daughter Lexi to the park and I've sat her on a swing. So I've pulled the swing up and the swing first travels 120 degrees. So if we imagine the swing's up here and it is going to go about to there, so about 120 degrees, then it travels back 90, travels back forward 60 and back 30. It then travels forward another 15 degrees before coming to rest. What is the angular displacement and the distance? So pause the video at this point and have a bit of a discussion in terms of what you think. Okay, so first of all, the angular distance. So you've got to do 120 plus 90, which is 210, then plus 60, which is 270, plus 30, which is 300, plus 15, which is 315. So the angular distance is 315 degrees. However, what is the displacement? Now, you should remember from the linear lesson that the definition of displacement is a straight line from start to finish point. So with angles, it is the difference in the angle from the start and finishing point. So if we start at 120, which was say up here, we go down, we go back 90, go forward 60, 30, 15. So eventually, what I want you to imagine is I have let my daughter go from this angle here, from the right angle, and she's gone for the 120, and I haven't pushed her again. So eventually what's going to happen is the swing's going to come to a rest. So the difference from here down to here is 90 degrees. That is the angular displacement, because that is the distance from the start and finishing angle. Okay, so we've been talking a lot about degrees, and I talked in our first week about what we measure in, and I was quite pedantic about the SI units. So if you remember, I asked someone what they lifted, and they replied something like 120, and I jumped on that and said, what is that, pounds, is that tons, etc., etc. So you've got to be really pedantic in terms of what we measure in at this level as well. So we measure in something called radians, and that is expressed as rads. So just to give you an idea of what a radian equals, it equals 57.3 degrees. So there is 360 degrees in a circle. So just pause the video and take a minute to try and work out how many radians are in one circle. So there is 6.28 radians, or 6.28 rad, in a circle. So angular distance and displacement will be expressed in rad. Okay, so we need to know how to convert this. So there is an equation for us. So we've got the number of degrees multiplied by pi divided 180. So if you consider BODMAS, go back to GCSE maths, we need to put some brackets in here. So we got brackets here and here. Now what brackets mean is we have to do that bit first. So before we do the equation, you have to do pi divided by 180, which then makes the equation number of degrees multiplied by, then bracket, pi divided by 180, bracket. So now you've got this equation, I'd like you to convert the following angles into radians. So you're going to need a scientific calculator for this that has pi on it. Download it from either the Apple or the Android App Store, or if you can't find an appropriate app or you don't have the calculator, you can use 3.14 for pi. So pause the video at this point and see if you can work out the following problems here. Okay, so we're going to go through it together now. So I've got a free website with a scientific calculator on it. So if you were struggling to find an app, you can use this website too. So we're going to do the 200 one first. So if you remember the equation, it was the number of angles in degrees, which was 200. Then it was a bracket, and we use pi divided by 180. And you're going to close the bracket and press calculate. And that's given us, to two decimal places, 3.49. So hopefully you all got that. But I'm going to show you a really easy way of doing this as well through using Excel in Microsoft. So there's a command in Excel. What you do is you type equals, open bracket, and then start typing radians, and then you can double click on the command that comes up here. It's then prompting you to put the angle in. So our angle was 200, close the bracket, and you've got to close it again. Then press enter. And that's also given us 3.49. So you can use either way. Now, I much prefer Excel because it's much quicker. So for example, if we go back, we want it for 120. So if I go back here, I can update this equation. I can type in 120 there, and that's going to give us to two decimal places 2.09. And then if we go back again, we have 83. So I'm going to go back in here and change this at the top to 89 to 83. And that's given me to two decimal places 1.45. So hopefully you all got the same as well. So that's just a nice easy way to convert degrees to radians to make sure we're using the correct SI unit. Okay, so in our first week we did a big Usain Bolt case study. Now we're going to do one on Tom Daley also. So this is our case study here. So at the 2009 World Championships, Tom Daley performed a back somersault as part of his sixth dive. It took him approximately 0.4 seconds to complete the maneuver. So what I would like you to do is this here. So I need you to work out the angular velocity and the angular acceleration of Tom's full back somersault. So here's Tom here, and he's just giving you some advice by here. So first of all, remember to convert to radians. So your answer is going to come out in degrees, and I'd like you to put the answer into radians. So the formulae for linear and angular kinematics are similar. So for example, angular speed equals angular distance over time. So if I take you back to our first lecture, and I gave you these triangles here, so all you need to do is put the word angular in front of these. So angular displacement, angular velocity. So for example, if I wanted to work at angular displacement, I'd cover up this, and it'd be angular velocity times time to give me angular displacement. So find your notes from the first lecture and use them to produce your answers for this problem now. Right, so first thing we need to do is work out the angular velocity of Tom's full back somersault. So let's go back to the question to work out what we need. So if we're working out angular velocity, this is angular velocity here. We need to know the displacement, and we also need to know the time. So Tom's done a full back somersault, so we know it's 360 degrees he's gone through. And it's also taken him 0.4 seconds. So if we go into our calculator online, so before we do this, actually just pause the video and give yourself an opportunity to try and do the problem yourself. So if you can pause it now. Okay, so we know Tom's done a full back somersault, which is 360 degrees. And then we need to divide it by 0.4, which was the time to complete the dive, which equals 900. So if I come to a Word document, I'll track it first now. So 360 divided by 0.4. Sorry, 0.4 equals 900. However, you will remember me first week being quite pedantic about SI units. So I asked an individual what the bench press best was, and they said something along the lines of 120. And then I jumped on that and I was like, what do you mean? Do you mean pounds, grams, tons, etc., etc.? So you need to ensure that you're using the right SI unit. So the right SI unit for this is degrees, which would be a little dot above there. However, as I just told you, we don't use degrees when we are measuring angular velocity. We use radians. So what we're going to do now is come into here, and we are just going to put in 900 degrees in here. It's going to give us 15.7.1 to 2 dp. So if I come back here now, we're going to change this to 15.71, and then we'll change that to rad seconds and -1. This is our correct answer at the minute. So you could actually change that 360 to 6.28, because that's how many radians are in a circle, and he did a full back somersault. Now we've got this answer, we can now work at the next problem. So the next problem was angular acceleration. So if we go back to our lecture slides from the first lesson, so calculating acceleration is change in velocity or speed divided by time. So first of all, we needed to understand what this term meant, which was change in velocity. So change in velocity is equal to final velocity minus starting velocity. So if we go back to Tom Daly, Tom Daly was doing a back somersault, so his starting velocity is actually 0. So if we do final minus 0, if we go back in here, final minus 0, it's just going to equal 15.71, because if we do it properly, 15.71 minus 0, and we divide that by 0.4. So if we do BODMAS again with the brackets, 15.71 divided by, minus 0, it's just going to be 15.71 divided by 4. So when we go back into our calculator and we do 15.71, we're going to divide that by 0.4, calculate that. It's going to come out to, if we do 2 dp, 39.28. So that equals to 39.28, and if we do the SI, it is rads per second to the -2. Don't forget it's negative to the -2 because we're taking two velocities into account. Even though the starting velocity is 0, we're still taking that into account. So that is what that equals there. So hopefully when you're doing this, you were coming to, you were getting the same answers as me. If not, rewatch the video and just make sure you pause it at the appropriate points. Next week we're going to move on to kinetics. So kinetics, as I said in the first lecture, they change slightly different from kinematics because kinematics don't take into account force, whereas kinetics do. What I'd also like you to do is to read around the subject area using our two leading textbooks, which are in our module handbook. So they are Bartlett 2007 and Hay 1993. Both are available here at Bridgewater and Taunton College from the library. I can also signpost you in the right places if you'd like to purchase these textbooks as well. Any questions, please feel free to email me or to ask Max. Thanks for listening.